So now that we've learned about electricity, we're now moving on to magnetism. Magnetism is a very fun topic. There's a lot of things to cover, but we're just going to go through a brief overview of the different subtopics within magnetic fields, forces, and electromagnetic induction in Chapter 8. And then we're going to use that knowledge, combine it with the electricity knowledge we had before, and take a look at specific applications. So in Chapter 4, we're doing an introduction to magnetic fields. So what are we going to talk about in this chapter? First, I'm going to do a quick recap of circuits because they will come in handy, especially in Chapter 8. We're going to take a look at magnetic force and field, their definitions, equations, and how to apply those laws. We're going to take a look at magnetic force on a current. Most importantly, there are two Maxwell's equations that we haven't covered yet, Ampere's law and Faraday's law. We're going to take a look at Ampere's law and then take a look at Faraday's law in Chapter 8. So we'll focus on Ampere's law here and take a look at different types of magnetic matter. Then we're going to move on to different applications. We'll take a look at magnetic fields around an axon, magnetocardiograms, as well as magnetoencephalograms. So these are three different applications of magnetic fields that we can take a look at related to medical and life physics. Okay, so Chapter 7.1, Circuits Review. There were various different topics taught within that chapter, including the microscopic versus macroscopic views of current and Ohm's law, taking a look at current density, resistivity, and conductivity. Afterwards, electric power, resistance, and Kirchhoff's laws for circuits. So in brief, we took a look at the microscopic and macroscopic views of electric field versus voltage. And basically, when we're taking a look at the microscopic view of things, we take a look at small components within a larger piece. So for example, if you have a changing current across a conducting substance or a material, and you have to break it down into tiny little pieces, just like we did with electric fields with dE and dQ. That's when you take a look at the microscopic view of things. So that's where current density comes into play, because maybe there's a different amount of current passing through each small portion of the conductor that you have. If everything is constant and you already know that you have a uniform current density, then you can move on to a macroscopic view where I is equal to J times A. In that case, you just have one constant current flowing throughout the whole circuit that you have, or the whole system that you have. Similar with resistivity, you have rho representing resistivity. If there is a different resistivity for each section of your object, then you have to take a look at that. It is a property of a given material. If you have different materials within your conductor, then there are different resistivities. Otherwise, you can take a look at a uniform cross-section, which should have a consistent resistance in the macroscopic view. And of course, based on which one you take a look at, whether it's microscopic or macroscopic, you have different ways of representing Ohm's law. So you can have J being the current density, being equal to the electric field over resistivity, or you can have current is equal to voltage over resistance. So these are the two main versions of Ohm's law based on what kind of system you're looking at. So some key equations. You have the equation for I for a microscopic current given by delta Q over delta T. If you have a small piece of Q over a small piece of time, then you can take a look at this and you get this equation from a small piece of what you're looking at, including a cross-sectional area. You have Q, and then you have the drift velocity. So I won't go into all the details about that. You have the current defined by the current density, NQ VD. And there are various different ways of representing the current density. You can have sigma times E. You can have resistivity, where sigma is equal to conductivity. And of course, another view of Ohm's law. Now for the macroscopic view of things, that's usually the equations we use when we're taking a look at circuits. You can use I equals to V over R, various different ways of representing electric power. And then of course you have terminal voltage. When you're taking a look at a system with internal resistance, just make sure you subtract the original voltage, or you subtract the internal resistance from the overall voltage. Now, of course, we took a look at circuits and components. So back then we took a look at capacitors and equivalent capacitance. The last topic, we took a look at equivalent resistance. It's basically got the opposite trend as capacitance. So if you have resistors in series, you're just going to add up all the resistors and their resistance. If you have resistors in parallel, then you're going to add them up in a reciprocal fashion to get 1 over the equivalent resistance. And finally, Kirchhoff's rules. So these are important because they help us determine the resistance, the current, and the voltage across each individual component of a circuit based off of rules at the junction points and the different loops within a circuit. So just remember the 2 different rules. For a junction rule, basically at every single junction of over 3 joints or 3 wires coming into it, you have to make sure that the total sum of the current is equal to 0. So there should be an equal amount of current going into the junction as there is coming out of the junction to maintain consistency along the uniform current. You have Kirchhoff's loop rule. So no matter what loop you look at within your system, if you have a loop, then the algebraic sum of those potential differences must be equal to 0. So in that case, all of the voltage going into the circuit must also come back, and it all has to add up to 0. Okay, moving on to magnetic fields. We're going to go through an introduction, a definition of what magnetic poles are, and the importance of magnetic fields. So in terms of the big picture, magnetism is really just anything that involves a moving electric charge. Back then, when we were taking a look at electricity, we took a look at electrostatics. So basically what happens when a charge is just stationary and not moving. Then we can use Gauss' law and all those different laws that we talked about to either get the electric field, the electric force, or various different types of measurements. Now, with magnetism, we look at a moving electric charge, and that means that you have a magnetic field. It's the interaction of magnetic forces. So when an electric charge is moving, it becomes the source of a magnetic field, and the moving electric charge is what responds to a magnetic field as well. So in one sense, you have a moving electric charge that becomes a source of a magnetic field, and that magnetic field will then also affect the movement of other electric charges. Then we have magnetic force. It's a force that the electric charge experiences when it's not moving parallel to the field. Basically, when you have a maximum amount of force, that means the charge is perpendicular to the field. Now, for magnetic poles, this should be a recap of various different courses that you've taken before, even from high school. So opposite poles attract and like poles are going to repel, basically like electrostatics. So if you have a north and a south pole, they are going to have an attractive magnetic force. If you have 2 norths or 2 souths, they're going to have a repulsive force. In terms of the Earth's magnetic field, I just wanted to mention that based on what we have for the magnetic field, we can assume that the Earth has a north pole and a south pole. So in terms of having this somewhat bar magnet right in the middle of the Earth, you can then create a general outline of what the magnetic field looks like around the Earth. So these magnetic field lines are going to show the direction that a compass would point at a given location. So if you're sitting over here in Canada, then you're going to have the compass point towards the north. So keep in mind, there's a south geographic pole where the North Pole is from this internal bar magnet, and then you have a north geographic pole where the south part of the magnet is pointing. So just keep that in mind. It's the opposite of where that internal bar magnet of the Earth is. So where can we find magnets and magnetism? Pretty much in all electronic devices. One example is an audio speaker. I like this because I like movies, and depending on what kind of setup you have, the different types of connections and circuitry within certain speakers gives you a different type of sound. So audio speakers contain an electromagnet. It's a metal coil that creates a magnetic field when an electric current flows through it. So the coil is going to act as a permanent magnet, and that's something we'll take a look at near the end of this lecture, where there's different types of magnets. And the other electromagnet is mobile. So just keep in mind, there's a coil that stays where it is, and then there's another electromagnetic that is mobile. So the electromagnet is attached to a flexible material, and it vibrates when the current goes through that coil. So in other words, every time an electrical signal goes through the speaker, there's current flowing through the coil right here. And this coil is considered the permanent magnet because it doesn't move. But there's another magnet that's mobile up here, and it vibrates. It vibrates because there's going to be an attraction or repulsion every time a current passes through this permanent magnet in yellow here. So we attach something flexible to the mobile magnet, and we add a cone of some sort, like this cap over here, to amplify the sound that comes out of the speaker. Next, we want to take a look at where we can find magnetism in living things. So we took a look at speakers. There are so many more applications, but let's take a look at where we can find it in living things. And when we talk about that, we take a look at bacteria, specifically magnetotactic bacteria. So these are really unique organisms because they orient themselves and they move along magnetic field lines, which is pretty cool. It's possible because within the bacteria themselves, they have something called magnetosomes. They are small organelles made of magnetic iron material wrapped in a membrane. These bacteria synthesize nano-sized magnetic particles that function as a compass needle. So we're going to take a look at this later on in the lecture. But basically, there's about 10 to 20 magnetosomes within each microbe, and every single one contains a magnetic particle and are chained together to create a magnetic dipole. So it's not just one of these, it's multiple of them, and they're always in chains, and they all line up within the bacteria itself to create something like a compass needle. So all these bacteria usually have a flagellum, which they use to help with mobility after being oriented in a certain direction. A good question is, where are these bacteria found? They're commonly found in freshwater and marine habitats. They're mainly anaerobic microorganisms that prefer aquatic environments that contain little to no oxygen. So they're really found in deep waters. And it's because of this that a lot of people think that, and a lot of researchers think that magnetotactic bacteria represent some of Earth's earliest inhabitants, just because they don't need the oxygen and they live in the depths of the ocean. So we'll take a closer look at this later on to see how they actually respond to the environment and how they can use the Earth's magnetic pole to move around. Okay, so now we're into magnetic forces and fields. Basically in this topic, we'll go through what a magnetic force is, what a magnetic field is, how to define them mathematically, and then take a look at the electromagnetic force, because finally we can put everything together. Then we're going to take a look at charged particles and magnetic fields. So the magnetic force has the following characteristics. It's always perpendicular. So over here, we take a look. We have the we have B over here representing the magnetic field, and the magnetic force is F, and you have velocity v of the charge. So keep in mind the magnetic force F is always going to be perpendicular to both velocity and the magnetic field. So you have velocity going up over here, B pointing out. It means F is going to go towards this way. The magnitude is then going to be proportional to the product of the charge itself, Q, the speed V, and the field strength B. And that means the greatest value is when the charge is going to be perpendicular to the field. So you have this, FB is equal to QV crossed with B. We now have a cross product, which means we have QVB sine of theta, where theta represents the angle between V and B. Now, the most important part to this is being able to figure out the direction of the magnetic force. So if we curl our fingers in the direction that would rotate V onto B, we get the direction of the magnetic force. So in this example, well, we basically see, let me see, gotta use my left hand because the picture is reversed. So if I have V pointing towards the left side of the screen over here, I'm going to curl. That's good. I have to use the right hand actually, but it's reversed. So if I have V over here, I use my right hand, and I have V over here. I know it's reversed, but if I have V pointing in this direction where my fingers are, and B is pointing out of the screen towards me, I curl my fingers towards B, which is coming out of the screen, and my thumb is going to point up. And that thumb's direction up is going to be the direction of the magnetic force. So just make sure you use your right hand for that. So we're just going to take a look at a few scenarios over here just so that we can familiarize ourselves with what's happening. Let's take a look at what happens when the charge is parallel to the magnetic field. If the charge is moving parallel to the magnetic field, so basically like this, if I have if I use my right hand and V is the direction of my fingers, I can't really point my fingers or curl my fingers towards B. It's simply just going to be in the same direction. And in that case, I don't know where my thumb's going to go. It's going to have a zero magnetic force. If you don't want to use the thumb rule, another simple way to think about this is for the sine of theta, for a cross product, if you have two vectors that are parallel to each other, sine of 0 or sine of 180 is going to be 0. Now let's take a look at what happens if your charge is at an angle. So simply put, just use the cross product and you have QVB sine of theta or sine of phi. You're just going to get a portion of the magnetic force if it were perpendicular. And of course, if you have B going in this direction, then at least we would still be able to figure out the direction of the magnetic force because you can use the right hand rule where V is pointing this way, you're curling your fingers towards B, and that means your force is going to be up. Now, the next scenario, what happens when the charge is moving perpendicular to the magnetic field? Then that is going to give you the maximum magnitude of force because sine of 90 gives you 1, and that gives you all of QVB together. So V and then B and then up for your right hand rule. Now, keep in mind, the right hand rule that we just showed is good for a positive charge Q. So an example here would be whatever direction your charge is going in, you're going to curl your finger towards the direction of the magnetic field, and that's the direction of F. But what happens if you have a negative Q? In that case, if the charge is negative, you still use the right hand rule, but whatever answer you get, it's the opposite because it's a negative charge. So let's take a look here. I have a negative charge, but my charge is moving along this green vector, V. So I have B going this way. I have to curl my fingers towards B, which is going towards the right, and my thumb is going to point up. Because it's a negative charge, I'm just going to reverse it and it's going to go down. So that would be the direction of the magnetic force. Another example is the one below. So basically I have my fingers pointing towards V over here. So it's something like that. B is towards the right this time. I can't really curl this way. I gotta curl this way. And so my thumb's going to point down. But it's a negative charge, so I flip it and the magnetic force goes up. Next, we're going to take a look at the units of electromagnetic force and basically what the EM force is. The units of a magnetic field are Newton seconds per coulomb meter. Basically, we can just call that a Tesla, named after Nikola Tesla. 1 Tesla is actually a very, very strong field. We can use Gauss G, which is equal to 10 to the negative 4 Teslas, to conveniently refer to smaller units of field. Now, when we're using Gauss, just keep in mind, if you're doing a comparison between Gauss and Tesla, any application that uses Gauss will usually have a lower magnitude of magnetic fields. If you're using an application with a large quantity of magnetic fields, like an MRI machine, then you're going to be using Tesla, and that's a very, very strong magnetic field. Now, because we have taken a look at electricity and now a little bit of magnetism, especially electric force and magnetic force, if there is a system that has both, we can combine the two of them and come up with the electromagnetic force. We know that F is equal to QE, and we also know that F is equal to QV crossed with B. So based on these two, we have the magnetic force and we have the electric force added together to give you the electromagnetic force. Another thing to keep in mind is that the magnetic force depends on velocity, but the electric force does not. We can actually cancel out the magnetic and electric fields, so B and E, to be able to select a certain velocity for our application. So moving on towards what's called a velocity selector, we can actually cancel out the B and the E, as I mentioned before, and basically have V equals to E over B. So why would this happen? It's because if we can set up a system where QE is equal to QVB, we'd be able to cancel out both of the forces and just end up with E over B quantities of the magnetic field. Okay, we are now going to take a look at charged particles and magnetic fields. So the magnetic force is always going to act at right angles to the particle's velocity. That part we already know about. It basically changes the direction of motion, but it'll never change the speed. So because of that, it does no work. If the particle moves at right angles to a uniform field, the magnetic force will have a constant magnitude. And we can actually try to calculate this. We take a look at the radius of the particle's circular path, and that's what we're trying to get. If V is perpendicular to B, then we know that the magnetic force is equal to QVB. But we also know that the magnetic force is equal to mass times acceleration. And if we set the two equal to each other, we get this. So QVB equals to MA, where A is equal to V squared over R. We then get R is equal to MV over QB. So keep in mind V squared over R is going to be the acceleration in circular motion. So we now know the radius of the orbit. What about the period of circular orbit in a uniform magnetic field? We're able to calculate this too, because all we need to find out is the circumference of the circular path taken. And that's just it's just 2 pi r for a circle. So the period is then going to be given by t equals to distance traveled over a certain amount of speed. And that gives us 2 pi r over here over v, which is equal to 2 pi mv over v QB. So then we can reduce everything and get t equals to 2 pi m divided by QB. So does this make sense? It does, because the greater the particle's momentum, mv, the harder it is for a magnetic force to bend its path, and the larger the radius. The larger the radius. So a larger charge or a larger field will increase the force and make a tighter orbit. So this equation is fairly important in terms of understanding the period and the motions of a particle within orbit. Finally, we take a look at cyclotron frequency. It's a unique type of frequency that's used to describe the particle's circular motion in terms of its frequency in revolutions per second. So basically, the opposite of the period we just took a look at. It's QB over 2 pi m. So that has a specific name called the cyclotron frequency. So in the next few slides, we're going to go through a few practice problems, and we'll be able to apply these equations. Okay, in this problem, we have a velocity selector that uses a 60 millitesla magnetic field perpendicular to a 24 kilonewton per coulomb electric field. At what speed will charged particles pass through the selector undeflected? So first of all, we should probably state our knowns. So we are given we know the electric field, or the magnitude of the electric field is 24 kilonewtons per coulomb. We know that the magnitude of the magnetic field is 60 millitesla. Now we have to ask ourselves, what is there an equation that can tie these two together? And there was. We know that there were equations for a velocity selector that came from the electromagnetic force. So we know that the electromagnetic force is given as F equals Fe plus Fb, which is equal to QE plus QV crossed with B. So in order for a particle to pass through, we have to set two things equal to each other. So in order for a particle to pass through, Fe must be equal to negative Fb. So that means QE, and we're just looking at magnitude here, is equal to QVB sine of 90. That means E is equal to VB, and V is equal to E over B. So that means we have 24 kilonewtons per coulomb divided by 0.06 Tesla, which is equal to 400 kilometers per second. So in problem 2, two protons moving in a plane perpendicular to a uniform magnetic field of 500 grays undergo an elastic head-on collision. How much time elapses before they collide again? So we first have to analyze the problem to see what we're trying to solve. First, both particles are identical in mass, so we have an elastic collision. So what is given to us, we know that we have an elastic collision has taken place. That means we have V1 prime is equal to V2, and V2 prime is equal to V1. So we also know that both particles have equal mass m. And the m is equal to 1.67 times 10 to the negative 27 kilograms. Now, the motion of each particle can be represented by a circle of radius. So motion represented by circle of radius r equals to mv over EB, where E is equal to the charge. The period is also T equals to 2 pi m over EB. So these were just from the notes. So now we're trying to solve and find how much time it takes before they collide again. So we are interested in looking at the period. So when we're solving, we just use T is equal to 2 pi 1.67 times 10 to the negative 27 kilograms. E is equal to 1.6 times 10 to the negative 19 coulombs. And we have 500 grays, which is 5 times 10 to the negative 2 Tesla. So we just have to make sure we're using SI units. Then we have 1.31 microseconds as the time that elapses before they collide again. Now that we've taken a look at magnetic forces and fields, we want to take a look at magnetic force on current. So we're trying to bring everything together. We'll take a look at the effect of a magnetic force on a current, and we'll take another look at the right-hand rule because we've added another component to our scenarios. So an electric current is going to contain charges in motion. That means that a charge in motion is going to create a magnetic field or generate a magnetic field, and that current is going to experience a magnetic force. So if a current I exists within a wire, then the charges are going to share a common drift velocity, Vd. So each will experience a magnetic force given by this equation. So it's basically just Fq equals to QVd crossed with B. Same as before. We've just replaced V with Vd for the drift velocity. Now, if the wire has a cross-sectional area of A and has n charges per unit volume in a certain length L, we can then redefine the total force because we're only taking a small portion when we're taking a look at Fq. So here we have F equals to, and we take a look here as NAL QVD. So the A and the L are going to give us that little volume element. Then we have N being the number of charges per unit volume. Then you have QVD for the total number of charges affecting the magnetic force. So from the previous chapters, we've learned that this equation, I, is equal to NAQVD, and that was the microscopic view of current. So we can immediately just apply that and replace those terms in the equation for force with I. So then you have F equals to IL crossed with B. And that's very important because now we have a succinct equation for the magnetic force on a current. So in this case, the force is perpendicular to both the current and the magnetic field. But there is a hand rule for this, and it's the right-hand rule revisited. So when we're taking a look at the right-hand rule, the direction of motion is no longer V. It's the way the current is flowing in the direction of L, the length element. So if the current is flowing along this blue line, then there's a certain magnitude of current I, and L just represents the direction of the current. So we're going to point our fingers towards L. So in this case, it's kind of going, let's see if I can do this, going this way. And then we want to wrap our fingers towards the magnetic field vector. So in this case, you have current going here, out. We're going to wrap it around towards B. So we have our fingers pointing this way. We wrap it around towards B, and then force is going to go up. So it's the exact same thing as before, except that we've replaced velocity V with L. Okay, so in this problem, a piece of wire with mass per unit length 75 grams per meter runs horizontally at right angles to a horizontal magnetic field. So let's first write down what we're given. So we know we have a mass per unit length, which is given as 75 grams per meter, runs horizontally at right angles to a horizontal magnetic field. So there are right angles involved. We have a current of 6.2 amps. And things are suspended against gravity. So we know that there are two forces at play. We know there's Fg and there's Fb. So because the wire is suspended against gravity, these two forces must balance each other out. So Fg must be equal to Fb. We know Fg is equal to mg, and we know Fb is equal to, for a wire, ILB sine of theta. And we know theta is equal to 90 degrees. So now we can put everything together, starting from Fg equals to Fb, and solve. So we have mg is equal to ILB sine of theta. But we know sine of theta is just equal to 1 because sine of 90 is equal to 1. So that means we have B equals to mg over IL. Now we know that there's m over L given to us already, so we can simplify this to 75 grams per meter times g, 9.81 meters per second squared, divided by I, which is 6.2 amps. And that's going to give us B equals to 0.119 Tesla. So now that we've been able to take a look at magnetic force, we want to be able to figure out how we can calculate the magnetic field. So there are various different ways of doing it, and just to sum up Chapter 7.5 and Chapter 7.6, which is the Biot-Savart Law first, and then Ampere's law, it's very similar to how we approached solving for the electric field. So if you remember, when we were solving for the electric field, one of the methods was to apply first principles to it. So we would break up the shape that we had into small differential elements, dq, and then we would eventually find out dE, which is a small differential element of the electric field, and then integrate to find the total electric field. Very similarly, we have the Biot-Savart law. It does the exact same thing, but we're trying to find a differential element of the magnetic field, dB. So the equation for dB, which we can use, is called the Biot-Savart law. But then these types of questions and these types of calculations do take time depending on the system you have and the shape of the object that you have. So there's a better way of doing it. For electricity, we had Gauss' law, and for magnetism, we have Ampere's law. Whereas we were looking at the total enclosed charge for Gauss' law, we're then going to look at the total enclosed current for Ampere's law to calculate the magnetic field. So we're first going to start off with the Biot-Savart law because it's first principles. Now, first, we want to go through the origin of the magnetic field, just so that there's a little bit of history involved. In 1820, Hans Christian Ørsted discovered that a compass needle is deflected by an electric current. So there was that connection between current and magnetism. A month later, Jean-Baptiste Biot and Félix Savart experimentally determined the form of the force arising from a steady current. So from these experiments, they showed that electric currents can create magnetic fields. So a lot of our efforts in terms of calculating a magnetic field will come from knowing and understanding the current within the object. So then we take a look at the Biot-Savart law. The Biot-Savart law gives the contributions dB to the magnetic field at a point P due to a small element of current dl. So with magnetic fields, we have dB and dl. For electric fields, we had dE coming from dQ. So keep in mind this as a vector quantity. for magnetic fields, and we can represent this in a vector equation. So the Biot-Savart law is given as dB equals to mu naught over 4 pi times I dl crossed with r divided by r squared. So looking at this equation, the first thing we usually have to tackle is the cross product. Once we have that, then we can integrate properly and figure out our magnetic field. So just to explain using another diagram, we have a current carrying wire with the current going up along the wire. Remember, the direction of the current is going to be represented by dl, and that dl is also going to represent a small differential length element of the wire. So we have this arrow going up along the current carrying wire. We then want to figure out the magnetic field at a point P over here, a distance r away. This r is the r in the denominator in the Biot-Savart law. Then we take a look at r hat. Because we have a cross product, we need our second vector, and that second vector comes from the direction from dl, that differential length and current element, towards that point that we're looking at. So r is going to be directed towards P from dl, and the angle theta is going to be between dl and r. So the maximum amount of force that we're going to experience is when these two are perfectly perpendicular to each other. So next, after you have set up the equation for the Biot-Savart law and have dB, we just have to integrate in order to get B. Usually the first thing we do is factor out mu naught over 4 pi, and then we have this to take care of. So in general, this means that the magnetic field lines are going to encircle the current that is their source. And of course, we really like our right-hand rules for magnetism. We're going to take a look at another one. If we want to figure out the direction of the magnetic field or the current, the thumb is going to point along the current, and then your fingers are going to wrap in the direction, wrap around the wire in the direction of the magnetic field. So just keep in mind, if you're given a magnetic field and it's, let's say, counterclockwise from above, then you're going to wrap your hands around in a counterclockwise fashion, and your thumb is going to point in the direction of the current. Likewise, if you're given the direction of current, all you have to do is point your thumb in the direction of the current and then see where your fingers wrap around to get the direction of the magnetic field. Now that we know how to analyze what happens with one wire, there are going to be scenarios when you have to analyze the contributions from two wires that are carrying a current side by side. So what happens to the magnetic force between conductors? Here we have two parallel wires with parallel currents, a distance d apart. They each have a magnetic field. So in order to get the magnetic field, you can do the right-hand rule for current carrying wires. Do this. It's going to have a magnetic field going this way. Same, we have a magnetic field going down. In between the two of these, though, you see that the magnetic field goes up from the left wire and the magnetic field goes down from the second wire. So in terms of this, we should probably figure out the magnitude of each of these magnetic fields. The field of wire 1 at the location of wire 2 is given by B1 equals to mu naught I1 divided by 2 pi d. The field is then perpendicular to wire 2, so the force on a length L of wire 2 is given by as follows. So this is then going to be the magnetic force between two wires, given by I2L crossed with times B1. So taking a look at this, we can see that if you have parallel currents, they're going to attract. Because here we have two parallel currents, and we know that the force is going to be pointing towards each other, so they are going to attract. This means that if we swap one of these currents and turn it into the opposite direction, then that means that the currents are going to repel, or the two wires are going to repel. Another thing I want to mention is that the force between conductors can be quite large. Think of the hum that you hear when you're close to electronic devices. So engineers who design strong electromagnetics have to provide enough physical support to withstand a magnetic force and to contain the amount of power that's stored within. Okay, so now let's take a look at the field of a current loop. We are now looking at the Biot-Savart Law, and it can get quite complicated fairly quickly. So we're trying to find the magnetic field at an arbitrary point P on the axis of a circular loop of radius A carrying a current I. So we're going to use the exact same approach as we did for electric fields, where we had to break everything down into tiny pieces. So first, we do want a diagram. So we have our x-axis coming out through here, and I'm going to draw a blue circular loop. Like this. Now we're going to take a small piece of this circular loop. We'll just use the top part. And we're going to have to find the magnetic field at an arbitrary point P, we'll say here, on the x-axis. So that means, similar to before, we're going to need to know some kind of relationship from that small piece up top to P. We call this distance R. We know that there's going to be a right angle triangle here, and this is going to be X, where this point is given as 0. So next, there is a circular loop that carries a current of I. We're just going to assume the current is going counterclockwise, facing it from the right, and that means our DL would be like this. Now that we have R, we also know that this direction is R hat. So a few notes. The Biot-Savart law is going to determine the field at P, but we have to first identify the vectors dl and r because they appear in the law. So just remember that dB, the Biot-Savart law, is equal to mu naught over 4 pi. We have I dl crossed with r over r squared. So remember in our notes we said we have to first find out the cross product. So that means we need dl and r. And the last thing we need for this problem, which we can solve right now, is the direction of the magnetic field. So if I have dl going this way and r going towards P, where is my magnetic field pointing at P? So we can use the right-hand rule. And for cross products, we know that if you have D and L going this way, then most likely your B is going to go this way. So we have dB going this way. Now, this is only one small section of this whole circular loop. So if I went around the entire loop, then I would have a bunch of these dBs going around. All of them are slightly tilted forward, so that means that the overall magnetic field should be in the x hat direction. So an important thing to note is as you go around the ring, the YZ components cancel. And B is simply equal to BX. So now we can try to solve based off of our analysis of symmetry. We know that B is simply equal to the integral of dBx, so that's all we have to worry about. We also know that let's just go back a bit. We know that dB is equal to mu naught over 4 pi IDL crossed with R over R squared. But we only care about dBx. So dBx is only equal to dB cos theta. And we know that cosine of theta is equal to, so we take a look at theta, which is over here. Cosine of theta is equal to A over R. And we also know that R is equal to the square root of x squared plus a squared. So now with that, we should be able to figure out the cross product. So dl crossed with r hat is equal to, and this is fairly simple to solve. We know dl is perpendicular to r, so that means we simply have dl r sine of 90. Remember, it's the angle between these two vectors, so it's just dlr times 1. But also, we know that r is a unit vector. So the value of the unit vector is equal to 1. So we have simply dl. So we can go back and we can rewrite this as dbx. dbx is equal to mu naught over 4 pi. We have up top, we have IDL over r squared, which is just x squared plus a squared. But we also know that dbx, oh, sorry, one second, jump the gun a bit, shouldn't be dbx. So db is equal to that. After that, we take dbx, which is db cos theta. So then we have mu naught IDL over 4 pi x squared plus a, and cos theta is a over r, so we get a over x squared plus a squared, so the power of 1/2. So now we can solve. We know b is going to be the integral of dbx. So we can factor out all of the constants, mu naught I 4 pi a, we also know that x is a constant. We know that a is a constant. So these are all constants as well. So at the end, what we have is mu naught IA over 4 pi x squared plus a squared to the power of 3 over 2 times the integral of dl. And dl is the length of the ring. So we can easily just, so we'll just circle this and say the integral of dl is simply the length of the ring, and therefore you have 2 pi a as the circumference. So then we have b, let's change this to bx, is equal to, mu naught 2 pi a ia over 4 pi x squared plus a squared to the power of 3 over 2. And bx is equal to, let's see what, cancel, we have 2 pi. And I think that's pretty much it. So we have mu naught I a squared over 2 x squared plus a squared to the power of 3 over 2. And we know that it's a vector, so we have to make sure we say what direction it's in. So it's going to be in the x direction, and that would be our answer for the field at point P of a current loop. Okay, so now we want to take a look at the field at a certain point P of a straight wire instead of a loop. So we're trying to find the magnetic field produced by an infinitely long straight wire that carries a steady current I. So first of all, diagram and givens. For the diagram, we have a wire, so I'm just going to draw that wire, and it carries a current. So I'm going to assume the current goes this way, I, which means at a certain point we have dl. It's going to go this way. Oops. Should probably have that in the, there's dl. Okay, so we want a, because it's a wire, we can have our point P pretty much anywhere around the wire. So let's put this P over here. That's my point P. This basically means I have R going this way. So this is R, and then this has R hat. And we have a distance y away from the wire. So R is equal to the square root of, we can have this being x squared plus y squared. Now there's also an angle between these two vectors, r and dl. So I have to make sure this angle is labeled here. And in terms of the direction of the magnetic field, a little bit, we don't have to do a full analysis, but it's a little bit easier to think about it from another view. We can take a look here. If we had a current carrying wire and the current was going this way, then that means we use the right-hand thumb rule. Thumb points towards I and the fingers wrap around in the direction of the magnetic field. So we have this. Being the direction of the magnetic field. So over here, we can say that dB is pointing out. So now that we have this, we have to use the Biot-Savart Law to see the contributions of each small piece of dl. So I'm just going to put some notes here. We know that dB is equal to mu naught I over 4 pi. We know that we have dl crossed with r over r squared. And the first thing is to take a look at the cross product. So we have dl crossed with r hat, giving dlr sine of theta. Sine of theta is equal to, so we take a look, theta is here. We know that sine of theta is going to be y over r. Due to trigonometric identities, so we end up with y over the square root of x squared plus y squared. Then we have dB is equal to mu naught I dl sine theta, which is y over r cubed. So 4 pi x squared plus y squared, 3 over 2. So now that we have this, we want to solve for the field and analyze the result. We're going to factor out all the constants. So these are all constants. It's only dl that changes. And I'm just going to double check to make sure that's correct. Oops, so a little bit too fast. So even though there's x squared plus y squared, r actually does change. So as dl moves across that wire, your r value is going to change, but the y value is not going to change. So your x will be changing. So that's why only 4 pi can be factored out. So from here, we have b is equal to mu naught iy over 4 pi times the integral from negative infinity, because it's an infinite wire, of dx over x squared plus y squared to the power of 3 over 2. So why did I use dx? I could have used dl, but dl lies on the x-axis, so dl is equal to dx, and y is a constant. So moving on, we have b is equal to mu naught iy over 4 pi. We're going to have to break this up into the integral from negative infinity to 0. Plus 0 to positive infinity, the exact same thing. And then we're going to set a limit. We have the limit as t approaches negative infinity of t to 0 of dx over x squared plus y squared to the power of 3 over 2, plus a limit as t approaches infinity from 0 to t of dx over x squared plus y squared to the power of 3 over 2. When you solve for this, we're going to end up with mu naught iy over 4 pi. This is going to be the limit as t approaches negative infinity of x over y squared, square root of x squared plus y squared, from t to 0. And this is going to be the limit as t approaches infinity of x over y squared, x squared plus y squared, from 0 to t. Okay, so now we can solve, and we have b equals to mu naught iy over 4 pi. We end up with 0 plus 1 over y squared plus 1 over y squared plus 0, or minus 0 actually, not that it matters. And that is going to give us mu naught I over 2 pi y. So that would be your answer for the field of a straight, the magnetic field at a point P away from a straight wire. So now we're going to take a look at Ampere's law, and it's a much better technique to use when you have a certain enclosed current that you can quantify. So we'll take a look at how to apply Ampere's law and take a look at fields of simple charges and current distributions, then take a look at solenoids and toroids as extensions. So with Ampere's law, it relates the magnetic field to its source. In other words, it states that for any closed loop path, so over here, any closed loop path, the sum of the length elements times the magnetic field will be able to give the current enclosed within a loop multiplied by mu naught. This is Ampere's law. So it's really similar to the Q enclosed we had before with electric fields and Gauss law. And if we take a look at the 3 wires over here, the way to apply Ampere's law is if you have multiple wires with multiple currents, you create what we call an Amperian loop right here. And that Amperian loop, if we take a look from top down, we see this. So we have the plane of the Amperian loop that we've created, and we are able to quantify the current that's enclosed within that loop. So we have I1, I3 coming out and I2 going in. So you would have I1 minus I2 plus I3 to get your enclosed current. Now that you have your enclosed current, you'd be able to have I enclosed, as well as be able to evaluate your closed loop integral here. So this is a line integral around a closed curve. We're going to simply evaluate the integral of b dotted with dr, and then use the equations we have for this and this to solve for b. So once again, just like Gauss' law, we had to take a look at symmetry. In this case, we do take a look at symmetry as well, just so that we can factor out b, and then have the integral of dr as the total length of the path. So afterwards, we can take a look at either this scenario here or this scenario here, depends on which one you're more comfortable with. We can use symmetry to give us the direction of the magnetic field. So here are some fields of simple current distributions. We have the electric dipole and we have the magnetic dipole. So basically with a magnetic field, you would have something like this. For a point charge, it's impossible for a steady current. We have current distribution with line symmetry. So basically, if you have a current going through a wire, then you have circular magnetic fields going along the wire in a counterclockwise fashion when you're taking a look from this side, going towards it. If you have a sheet that carries a current, then you can also have a magnetic field. And in this case, you have a magnetic field acting parallel to the sheet itself. Whereas for an electric field, you have everything acting perpendicular to the sheet itself. Now, taking a look at solenoids, basically this is an extension of a current-carrying wire. If you have a current and you wrap it around over and over again, you will have a very unique distribution of a magnetic field. So a solenoid is basically a long, tightly wound coil. So the more loops you have, the more constant the inner magnetic field. The reason for this is because if you just have one loop, then if my current is going along that loop, I'll be able to draw my magnetic field lines encircling that loop along that whole circumference. If I have multiple loops like this, then that means the magnetic field is going to have to wrap around and be elongated at the ends in order to wrap around the ends of the loop or the coil. So as we extend the coil from here towards this, the longer the coil, the more the magnetic field is forced to have a larger radius of curvature so that it can go along and exit along the edges of that coil. That forces the center of the coil to have a more linear and constant magnetic field. So considering this, if we take an infinitely long solenoid, we can assume that the magnetic field B and the length L are pretty much parallel to each other. So basically, if we just look at this section of a large solenoid, and if we combine that with Ampere's law, it means that the integral of B dr is going to be equal to, number one, B is constant, and we can factor it out for B. And then we have the integral of dr, which is the total path length, which is just L. So then we have BL as our value for Ampere's law. But then you have n wires per unit length of L. So we can rewrite this to have BL equals to mu naught NL times I. So that would be mu naught Ni to replace our value of B. Or not to replace our value of B, to have mu naught I enclosed. So in terms of a solenoid field, we actually have a condensed equation. We have B equals to mu naught Ni for a solenoid. So that means as a cross-section, a lengthwise cross-section of a solenoid, we have a bunch of wires coiled within each other. So in this case, we have the wire coming out and then going in at the bottom. So it's kind of like this. And everywhere along this, we're just going to assume that these are going to continue perpetually because it's an infinite solenoid. And we are assuming that the magnetic field is constant and linear and uniform in between or within the solenoid itself. So when we're taking a look at this, we're going to enclose this small section with an Amperian loop. And so there are n turns per unit of length. So a length of L is going to encircle n 1, 2, 3, 4, 5 times L turns. Each of these is going to carry a current of I. So the enclosed current is then going to be equal to I for the current within one of these coils multiplied by n number of coils multiplied by the length L. So that's where you get the B equals to mu naught Ni for a solenoid field. And of course, what happens if you have a solenoid and it's curled in a circle? So a toroid is basically a coiled solenoid. And so that means you now have your loops distributed along a circle. And the magnetic field is then going to be confined almost entirely within the space enclosed by the windings. So you now have a core that has a very strong magnetic field in blue. So when we're taking a look at toroids, we're going to take a look at a perfect scenario when you have a perfect circle and it's very symmetrical. Combine that with Ampere's law, we now have the integral of b dr being equal to, we factor out b, and we have the circumference as the path length, so we have 2 pi r. Now with Ampere's law, it has to be equal to mu naught I. So we take a look at the enclosed current. It's going to be n turns of a coil, and that means we have n times I as the enclosed current. So for a toroid, we have a magnetic field equal to mu naught Ni divided by 2 pi r for the path length. And keep in mind that the toroid field is not uniform, so it decreases as 1 over r. In this question, a long straight wire of radius r carries a current I distributed uniformly over its cross-section. We're trying to find its magnetic field outside and inside the wire. So we don't really need a diagram in this case. We're just trying to find the magnetic field outside and inside, so we're going to break this up into two. Let's first start with outside the wire. So outside the wire, we know that when we're enclosing a current and we're using Ampere's law, then the total enclosed current is just the total current I. So using Ampere's law, for an outside current, we know that I enclosed or encircled is equal to the total current I. And that means we have the integral of b dotted with dr is equal to mu naught I enclosed. We know that the path integral for a loop of radius r is given as 2 pi r times b because the field is parallel to the Amperian loop. So that means we have mu naught I. Then there's b, which is equal to mu naught I over 2 pi r. And that's our answer for b. And it is a vector, but it's kind of just going around it's going around the wire, so it's hard to pinpoint an exact direction. Okay, next we want inside. If we are inside, then that means when we draw our Amperian loop, so now I do want a diagram, we'll use this for the current carrying wire. Originally, we had this as our Amperian loop on the outside, so that was for outside. Now we're taking a look at what happens if our Amperian loop is on the inside, and there's a current I going through this wire. This tells me that only a portion of the current is going to be enclosed, so therefore I'm going to have to redefine I enclosed as some sort of I times some sort of ratio. So it'll be the little radius of the green Amperian loop here divided by the total radius. So that's how much is enclosed. Now we can use Ampere's law again. use the exact same equation, BdR, it's equal to mu naught I enclosed, which is just I r squared over capital R squared. This gives me 2 pi RB equals to mu naught I r squared over capital R squared. And B is equal to mu naught IR divided by 2 pi R squared. And that would be around the wire. In this problem, we're going to take a look at an infinite flat sheet that carries current out of this page. The current is distributed uniformly along the sheet with a current per unit width given by JS. We're trying to find the magnetic field of this sheet. So first we want a diagram, just so we understand what we're looking at. We have a current carrying sheet. So let's just draw this. We're going to use red for the current. It's going to come out of the sheet towards us. And then we have a magnetic field. So if it's going out, we know that the magnetic field is going to go counterclockwise this way. So that means we have B going this way at the top and B going this way at the bottom. Okay, so next we want to see if we can use Ampere's law. So that means we have to choose a rectangular Amperian loop so that it runs parallel to B. So I'll use purple for this. The Amperian loop we're choosing is just going to be like this. And we can have it go parallel to B in this way. So just as a note, we have chosen a rectangular Amperian loop. That runs parallel to B. Some other things we know Ampere's law is exactly like Gauss' law, where we have to add up all of the different values from each side of the loop. So in the past, we took at circular Amperian loops, which is just one path, one circular path. If we use a rectangular path, it's going to be 4 sides. But so with the 4 sides, we have 1, 2, 3, 4. Which ones are going to count? We do know that it's going to be an application of Ampere's law. So apply Ampere's law. And we get the integral of B dotted with dr. And we know we have to consider the ones that are parallel. So we want to carry about 3 and 1, whereas 2 and 4 are going to be 0 valued. So paths 2 and 4 have BDR of 0. So we end up with a side length L for each. We know this is going to be BL from the top, plus BL from the bottom, and this is 2BL. So with that, we have to set this equal to I enclosed times mu naught, and we end up with 2BL equals to mu naught, and I enclosed is simply equal to the current per unit of width times the width, which is L, and we get 2B equals to mu naught JS, and B is equal to mu naught JS divided by 2. So that would be our answer for the magnetic field of this sheet. In this question, we're taking a look at current within an MRI scanner. So the solenoid used in an MRI scanner is 2.4 meters long and 95 centimeters in diameter. It's wound from superconducting wire 2 millimeters in diameter with adjacent turns separated by an insulating layer of negligible thickness. So we don't have to worry about that. Find the current that will produce a 1.5 Tesla magnetic field inside the solenoid. So first, we're going to state our knowns. We are given the fact that B, we already know this from before, B is equal to mu naught Ni for a solenoid. But the problem is we need to find N. We also know that B equals to 1.5 T, because that's what we're aiming for. So I have B, I have mu naught. I can come later because we were trying to solve for that. So we are trying to solve for I. But before we can solve for I, we need N. So that means I have to do an analysis to find N. So if I have my solenoid here, we know that it's 2.4 meters long, and it is 95 centimeters in diameter, or 0.95 meters. It's wound from, so if we zoom into each portion in here, it's going to be wound from a superconducting wire that's 2 millimeters in diameter, or 0.002 meters. So that means if I take a look at each coil and I cut it open, it's then going to be, if I cut it lengthwise, I'm going to end up with something like this. And that is 0.002 meters. So in terms of N is equal to the number of turns per unit of length. I know that the length is 2.4 meters, and I can divide it by 0.002 to get how many turns there are, and then the length is 2.4. Okay, so then that gives me 500 turns per meter. What next? Now we're going to solve for the current. We're going to find I. I is simply just going to be this equation rearranged. I is equal to B over mu naught N, which is equal to 1.5 T divided by 4 pi times 10 to the negative 7 newtons per amp squared. 500 turns per meter, and I get I is equal to 2.4 kiloamps. So that is how much current is required in order to create a 1.5 Tesla magnetic field inside the coil. So now that we've taken a look at the Biot-Savart Law and Ampere's law, and we know how to calculate the magnetic field, we can now take a look at applications and different types of magnetic material. So there are three main types of magnetic material we want to cover: ferromagnetism, para, and diamagnetism. So in terms of the different types, I just named them, but an electron is going to possess an intrinsic magnetic dipole moment that's associated with a quantum spin. And that spin is called the quantum angular momentum. So depending on what qualities the electron has within a specific type of material and how responsive it is to a magnetic field, you then get the different types of magnetic matter. So let's first start with ferromagnetism, the most basic of all the materials. We are most familiar with this because they are in compounds like iron, nickel, cobalt, etc., basically magnetic materials that we know of. And there are strong interactions with atomic magnetic moments that result in what we call magnetic domains. So there are areas where approximately 10 to the 17 to 10 to the 21 atoms who have magnetic moments that are all aligned in the same direction. So basically, if we take a look at the diagram on the right, we have domains that are randomly aligned, or in ferromagnets, we have chunks of atoms that have similar alignment within an external field. So if you apply an external magnetic field, then your magnetic domains within that material are going to align alongside that magnetic field. So an external magnetic field will have to be applied in order to align those domains. Otherwise, they are randomly aligned by nature. So then, based on this, there are two different types of ferromagnets. There are hard and soft ferromagnets. So a hard ferromagnet is going to be one that after you apply a magnetic field, it's going to maintain its magnetism. This then results in a permanent magnet. Some examples are credit card strips, CDs, etc. Things that after you apply a magnetic field, that information or that magnetic dipole within those domains, and they're going to remain even after you remove the magnetic field. Then you have soft ferromagnetics that after you turn on and turn off the magnetic field, it will lose its magnetization. So examples are, for example, let's say you're trying to write some information onto a CD. As soon as you stop that process and you turn off that magnetic field, that information is going to stop being written on that CD. Same with tapes and other types of devices where it's required to start and stop certain activities. So in terms of ferromagnetism and how effective it is and how it's affected by temperature, we have to talk about something called the Curie temperature. The Curie temperature is defined as a temperature where certain magnetic materials are going to undergo a sharp change in their magnetic properties. So it doesn't mean that it'll lose its magnetic properties completely. It'll just undergo a sharp change. So usually this Curie temperature is at about 570 degrees Celsius. And it's really important to know that this Curie temperature is the temperature where materials, in other words, lose their permanent magnetic properties. So they lose their hard ferromagnetism if they're a hard ferromagnet, but they may still be affected by induced magnetization. So that is fairly important because it means it doesn't mean that it can't be a magnet ever again. We can simply replace it by induced magnetism, which comes from current carrying wires or a current carrying object. So let's move on to paramagnetism. These are compounds that respond weakly to external magnetic fields. So permanent magnetic dipoles do exist, but they don't really interact strongly with each other like ferromagnets do. So this is a normal paramagnetic material with the different atoms with their magnetic dipoles. If you apply a magnetic field, they're going to align alongside the magnetic field that's applied. But when the magnetic field is removed, they go back to their random state. So in this case, this is called a paramagnetic material because it will lose its magnetism when you take away the magnetic field, and there are no domains of atoms that respond equally and strongly to the magnetic field. The third type of material is diamagnets. These have no intrinsic magnetic moments, so it's naturally non-magnetic, but they can have magnetic moments induced by changes in the applied magnetic field. So if you have a diamagnetic material in an external magnetic field and you change the strength of the external magnetic field, you will induce changes within the diamagnetic material. So that's just the third set of magnetic matter to be aware of. Okay, so differences between the materials. We have ferromagnetic, paramagnetic, and diamagnetic. So we have a comparison between what happens when there's no magnetic field and when we apply a magnetic field. When you have a ferromagnet or a paramagnet, both of the applied magnetic fields will cause all of the individual atoms' magnetic dipoles to align with the applied external magnetic field. With diamagnetic materials, it's a little bit different. There are no intrinsic magnetic moments, but if you apply an external magnetic field and change it, there's going to be an opposing magnetic field within the object, which causes the atoms to be aligned in an opposing manner to the original applied magnetic field. So that part is important to know. Okay, so we can finally move on to applications to life and medical physics. So we get to talk about magnetotactic bacteria again, but in depth this time. We'll take a look at the magnetic field around an axon and two applications to medical physics, magnetocardiograms and magnetoencephalograms. So looking at magnetotactic bacteria, for short MTB, so I don't have to say it too many times, the main characteristic for each of these types of MTBs is that they have intrinsic magnetotaxis, so basically movement based on its surrounding magnetic field. So the key thing with this intrinsic magnetotaxis is that it affects both living and dead cells. So it's important to know that if a cell has died within that bacteria, it still has those magnetic dipoles and it still has the magnetic material to help align the bacteria and allow it to move towards wherever it wants to go based on its magnetic field. So it was discovered in 1963 by Salvatore Bellini and also in 65 by Richard Blakemore. They basically found these types of bacteria within bog water, and it was primarily proteobacteria like Magnetospirillum magneticum. So how does it move? It moves through flagellar motion, and also most of these are gram-negative organisms. The different MTBs are going to have different arrangements of flagella or different types of magnetosomes within their gene clusters. So how are these magnetosomes arranged? We call this arrangement the nanocompass, where they all line up and point in a specific direction. So they don't each point in different directions. They all align properly within the bacteria itself in one sharp needle that points towards the direction of motion. So magnetosomes are aligned in a chain-like fashion, imparting a magnetic dipole to the bacterial cell. So in this case, I don't know which direction it's supposed to be in, but let's just say it's towards the right. The scale is 200 nanometers, but we have a cell within the bacteria and all of its magnetosomes are pointing towards one direction. So it is called a passive alignment because it's aligned to the Earth's magnetic field lines. Its preferred environment is what we call the OATZ, the oxic anoxic transition zone, where oxygenated water meets oxygen deficient water. So that is where it usually likes to thrive. The MTBs are going to try to move towards the OATZ, no matter whether they're slightly above or below the OATZ. So how do they move towards it? It's controlled by flagellar motion, as well as the direction in which it's rotating. So it could be clockwise or counterclockwise to go forwards or backwards towards the OATZ. So Because of this, it means that the location of the MTB within the Earth's hemisphere will govern its motion. It has an effect as the magnetic dipole within the bacteria will align itself based on its location and the Earth's magnetic field lines. So that means its location on the planet is very important. So let's take a look at MTB motion. The OATZ is part of the water, right here. The OATZ is part of the water column or sediment where oxygen concentrations are preferred by these MTBs. The dotted black arrows represent the direction in which the MTBs are swimming, and that's just the general guideline because they're just swimming towards the OATZ. So if there are MTBs above or below the OATZ, they're going to move down or up respectively. So the solid black lines, however, within each of these MTBs is their intrinsic magnetic dipole based on their location within the Earth's hemisphere. So in the northern hemisphere, they're going to align towards a pole. So then it's going to be directed this way. So these two, whether they're above or below the OATZ, within the northern hemisphere, the intrinsic magnetic dipole that the MTBs have are going to point in the same direction. It means that if we take a look at the MTB above, then the flagellar motion is going to go counterclockwise, let's say, to move the bacteria forwards towards the oxic and oxic transition zone. And that means below, because the magnetic dipole is pointing away from the OATZ, the flagellar motion is going to turn clockwise so that the bacteria moves backwards towards the OATZ. Similarly, we take a look at the southern hemisphere. In this case, we have the magnetic dipoles pointing to more upwards based on the Earth's geomagnetic field in the southern hemisphere. And so it aligns itself with the Earth's magnetic field. And that means the bacteria below the OATZ is going to go clockwise, which is backwards, towards the OATZ. And then this is just going to have their flagellar motion go counterclockwise to move towards the OATZ. So keep in mind that it's just the flagellar motion that determines whether the bacteria will move forwards or backwards. It's not necessarily the magnetic dipole within the bacteria. So next we want to take a look at your nerve axon and field lines within our neuronal cells. So this is a cross-section of an enlarged nerve axon. Basically, the electric current is shown in thin lines and the magnetic field is shown as wide bands. We're going to note a change in the B field direction. So in this case, it's going around. Let's say if we're looking from the left to the right, this is going in a counterclockwise fashion. And then suddenly over here, we have something happening in the clockwise direction. So that's the direction of propagation. And it's solely due to the different myelin sheaths within an axon. So we can actually use the Biot-Savart Law to calculate the magnetic field due to an action potential propagating down a nerve axon. We're going to assume that the axon is infinitely long, once again, to make our calculations easy, and assume that it's embedded in an infinitely conducting medium that's completely uniform and constant. So what we need to do is complete our model and determine what parameters to consider in our calculations. So in terms of the magnetic field around an axon, there are three components to the current that we have to worry about. The current in the surrounding medium, the current along the interior of the axon, and the small current coming out through the membrane. So how do we calculate the field due to an exterior current? The field dB from dI into a surrounding medium from an axon element is called dx. We're then going to take a look at the current in the external medium from a small element dx that flows uniformly in all directions as if from a point source. So to summarize, the first part is to use the Biot-Savart Law to find dB from di and from an axon element dx. And then we're going to find the current, and then we're going to calculate the magnetic field generated by a spherically symmetrical radial current. And that is going to be 0. So all in all, we take each of these things and we determine that the axon is very thin, so we can ignore any external current coming from dx. And that's because we made the assumption that the surrounding medium is infinite, homogeneous, constant, and isotropic. So based on that, we can solve for the magnetic field of an axon. We know that the current through the cell membrane gives a very small contribution to the magnetic field, about 1/10⁶, and the major contribution is from the current itself, from the ions. So we use the Biot-Savart Law, and these values, we start at a specific location, and we assume that the axon lies along the x-axis, and we can then perform several steps to get our cross product for Biot-Savart Law. So instead of using x dx, what we're trying to do is say we have a ds for a small contributing factor of our length element. So we find the product and we get dx y naught z. And the term in the denominator is then r cubed. We have this term. So I haven't derived all the steps. If you're interested in this, contact me after and I can walk you through it. But here, I really just want to show all of the derived portions for each of the required steps through the Biot-Savart Law, so that you can see how we can create a model and apply the Biot-Savart Law to get an expression for a magnetic field surrounding an axon. So basically, we're trying to find each of the individual components of the Biot-Savart Law. The first one was the cross product, which is determined to be dx y naught z. The next part is to find out the denominator, the r value, which is this. Then we have to create an equation for the magnetic field based off of the Biot-Savart Law. So we have mu naught over 4 pi. We have the y naught from before, which we can factor out. And then we have our cross product over our r squared. So additional calculations can be done to show that the current I is equal to this. And then we can combine everything together to get an approximate expression for the magnetic field along the z-axis around an axon. So this is a very general explanation of what can be done mathematically and theoretically to model the magnetic field around an axon. Now, if we take a look at things visually, we can also figure out different ways of looking at the situation. So this is just another way of expanding the equation from before, which of course, if you wanted to do calculations in, you would have to expand it to get an approximate value. So is there another way of looking at this entirely? Yes, so we can actually assume that the myelin sheath acts as a coil inductor. The myelin is going to wrap around the axon like a coil, a very long coil. And the spiral current inside the myelin generates a magnetic field. So we can actually use the right-hand rule to determine the direction of the magnetic field generated by the coil. So the current is going to go around and the magnetic field is going to be where the thumb points. So it's another right-hand rule based off of this application because we have a bunch of coils of large thickness. So you can then do an analysis on different sections of the myelin sheath between the nodes of Ranvier. So you're going to end up with a bunch of these. You'll end up with a bunch of these. So this is just one myelin sheath, but you have a bunch of them going along the axon. So you have, you can do your magnetic field analysis on 1, 2, 3, 4, X number of myelin sheaths. And you'll find that in order to generate and sustain an action potential, the myelin sheaths on the same axon have to have opposing spiral currents. So think about that and why. While the myelin sheaths, if you have two axons beside each other, if you have them side by side, then you have to have similar spiral currents to have positive mutual induction, which is something we'll talk about later on and have not covered yet. So just to recap, because it's important, for a myelin sheath and in between the nodes of Ranvier, if you're looking at the same axon, each adjacent myelin sheath along the axon needs to have opposing spiral currents in order to have an action potential. Whereas if you have two axons beside each other, your myelin sheaths, your spiral currents should be in the same direction so that you can have positive mutual inductance. So we now want to take a look at two applications of magnetic fields and forces to medical physics. And that would be first a magnetocardiogram. So a magnetocardiogram is when you're trying to measure magnetic fields in order to diagnose a disease. So I have a comparison here. On the left side, we have an electrocardiogram. It basically measures electric potential differences. And in order to take an electrocardiogram, it's very difficult on a baby because the vernix is going to, over here, the vernix is going to shut off almost all of the electricity. But for a magnetic field, we are able to calculate everything. The magnetic field is not affected by the fluid within the womb. And so therefore, a magnetocardiogram is a good option when you're trying to diagnose anything for a fetus developing in the womb versus an ultrasound. So you have the choice of an ultrasound, or you can choose a magnetocardiogram to diagnose any heart conditions within a fetus. So keep in mind the vernix is actually the white coating around the fetus to protect it. It's this coating around, so in yellow over here. So how does magnetocardiography work? So it's actually quite complicated. It's a technique that measures the magnetic fields produced by the electric currents in the heart using extremely sensitive devices. So one example is a SQUID, which is a superconducting quantum interreference device. So basically, a map of the magnetic field is obtained over your chest, like this. And you're going to use mathematical algorithms to help locate the source of activity, or specifically, abnormal rhythms coming from the heart. So the signal itself includes three components, which may be displayed in either a scalar form as a function of time, or in the form of vector loops with one lead as a function of another. So no matter which method you choose, you have to choose a magnetic heart vector as the basis of the clinical MCG system. So what is the magnetic heart vector? We'll explain this in the next few slides. First, you have lead measurements. So just like the electrocardiogram, for a magnetocardiogram, you still need leads and you still need to take recordings. But the analysis required is a lot more complicated. So this diagram simplifies all of the steps and it still looks complicated. Number one, the activating cardiac cells act as a source element with current density J, which produce two fields. You have your electric field and you have your magnetic field. In this case, it's represented by H and not B. So there's two fields we have to take a look at. And basically, it gets split up into these two to see whether you have dipole, multiple dipoles, or a multipole to analyze. The third step is to take a look at the inverse problem. And the inverse problem essentially means, when you go down to step 4, you have to solve for the source based on the detected fields. So we're kind of moving backwards. We use a source to measure the electric and magnetic fields, and we use the results from this to solve for the magnitude of the source. And afterwards, you would go back up here. The inverse problem is then solved by creating multiple simplified models. to represent the properties of the source and the conductor. So first, the equations of the E and M fields have two terms representing the contributions of the source and the conductor. Then you have a clinical ECG lead, which provides solutions of the field equations with certain source and conductor models. Then you have in an MCG, the same model can be used as in an ECG. So here we have a magnetic field. The most important thing is to be able to take a look to see whether you have a dipole, a multiple dipole, or a multipole, to see if you have a trivial solution, a finite homogeneous, or a finite inhomogeneous solution. So once you have broken down everything into its individual components, you can then take a look at the lead systems to detect the electric and magnetic dipoles, and they each have orthogonal components because of the cross product. So at the very end, you should be able to have a sensitivity distribution of the electric field, as well as a distribution of the magnetic field that you can use for further calculations. So for us, that's a lead measurement, which gives you both an electric and magnetic field. For the purposes of a magnetocardiogram, you would just be focusing in on the magnetic field component. So taking a look at the next step, we're now taking a look at how we can map out the magnetic field. So in MCG, the mapping of the magnetic field around the thorax has been a research tool. If we use this mapping method to register the X component of the magnetic field around the thorax, then we'll be able to get all of the other quantities as well. So in terms of doing this calculation, we have to use something called a standard grid. So before I move on to the standard grid, I just want to explain this a little bit more. Basically, the similarity between the lead fields of certain electric and magnetic leads are illustrated in this diagram. So we have the E field, and then we have the magnetic field, basically from that previous slide we were on. If the magnetic field is measured in such an orientation, in the X direction in this example, and location, then the symmetry axis is located far from the region of the heart. The magnetic lead field in the heart's region is going to be similar to the electric lead field of lead number 2 in this diagram, which is oriented normal to the symmetry axis of the magnetic lead. So here's the magnetic lead, and then here is the ECG from lead 2. So the E field is going to be perpendicular to the magnetic lead. So this similarity may also be verified from the similarity of corresponding detected signals. So when we're taking a look at the 6-point grid or 6x6 grid, a natural method to measure the magnetic dipole moment of a source located at the origin is to measure the X, Y, and Z components of the magnetic field corresponding to the corresponding coordinate axis. Not corresponding axis. These may be either A, unipolar, so we're only taking a look at unipolar measurements, or we can take a look at bipolar measurements. So in our case, we're going to focus more on the bipolar measurements in the next slide. So if you want to take bipolar measurements, we call that the Bawley-McPhee lead system. It actually helps make a bipolar measurement of the equivalent magnetic dipole of the heart. Then you get all of the magnetic dipoles for each of the 3 coordinates of the XYZ coordinate system. So the general construction of the measurement system is presented in this diagram where you have an X. The body is placed in between these 2 silver X's, and the measurement of the X component of the magnetic heart vector, which is vertical, let's say, is going to be in between the yellow coils. So if I want to measure the X component, I activate these coils to induce a magnetic field, and I take measurements from the leads to see how my body responds to those magnetic fields. And then I get the X component of my magnetic heart vector. If I want the Y component, I turn on the Y or the red the red coils to induce a magnetic field to see how that affects or how my heart responds to the applied external magnetic field. Similarly, I can do the same thing with the z-axis. If I want the z component, then all the blue coils are going to be activated to induce a magnetic field. So that at the end, I get an x, y, and z component to my magnetic heart vector. So how do we apply and how do we symbolize this through a diagram? We use these to represent the coils. And so for an x, y, and z system, these two are the y coils, these two are the x coils, and these two are the z coils. So this bipolar arrangement provides a good lead field uniformity, and the only difficulty that arises is in locating all the magnetometers and being able to position them correctly around the body. So in terms of a drawback, the measurement of the component along the z-axis here is difficult because the z-axis is from the foot to the body, but if we want to figure out the magnetic heart vector along the length of the body, this one over here, the foot side of things, has to be elevated slightly because your body's blocking it. So you can have everything off from the top of the head, but you have to have a slight angle for the foot portion. So when you're taking a measurement along the y-axis, so from here and here, the other drawback is that your heart's kind of in the middle and you have to have a significant separation between the two detectors. So they have to be placed far away from the source. Whereas the X is the easiest because you can get as close to the chest as possible towards the heart. So how many magnetometers are required for the Bally-McPhee lead system? It's 6. 3 magnetometers or 3 pairs of magnetometers for each of the coordinates. Here's also a generation of the MCG signal. It's a schematic illustration of how the X component, so we see it's only the X component here, how the X component is generated within the MCG signal. So we take a look at the current that's going, and the current is then going to induce a magnetic field, and then it's going to respond to the applied external magnetic field as well. So what does a magnetocardiogram look like? It looks something like this. It's an averaged value of the same subject as in the previous figure. So this signal over here can be processed to give you something like this or like this. So for each of these, you have the Z component, the X component, and the Y component. Here you have XZ, here you have YZ, and here you have XY. So based on these three, you can create one of these sagittal, frontal, or transverse cross-sectional graphs of your magnetic heart vector, or you can combine all of them and get a signal like this for analysis for X, Y, Z, and M. So what are the advantages of MCG? It's because the sensitivity of MCG is not affected by the high electric resistivity of your lung tissue. It makes it possible to record from the posterior side of the thorax and the posterior side of the heart. And it also allows for the safe recording of electrical signals or magnetic signals from a fetus. The other thing is that your magnetic detectors are not going to be in contact with the subject, so there's no need for all those leads that are required in the EKGs. So now we want to take a look at magnetoencephalography, or MEG. It's a functional neuroimaging technique for mapping brain activity, very comparable to the EEG, electroencephalography method that we talked about before. But of course, the method of operations is going to be much different. So what it does is it records the magnetic fields that are produced by electric currents that take place naturally in the brain. So in order to take these measurements, you have to use very sensitive magnetometers, usually what we call an array of squids. So in terms of this, you have all of your currents going through your dendrites and your axons, and that is going to have an effect on the magnetic field. And we can measure these magnetic fields through magnetometers. So where do these origins of MEG signals come from? So first, we can take a look at an axon over here, and as the current goes through, you're going to have extracellular or volume currents going around. Then from this, we're going to take a look at this diagram over here. You have your charge moving along the axon, and that's also going to generate currents going along this way. From these currents, you have an induced magnetic field, and you have B going this way. This is what we measure in blue, and so the squids and the cap around your head will be sensitive enough to capture these slight and very faint magnetic fields coming from the flow of charge through an axon. So what are squid sensors made of? There are 306 independent measurement channels. They're organized in channel triplets on 102 silicon chips. There's 2 planar gradiometers and 1 radial magnetometer. So what are some typical signals that show up from an MEG? So if you have any type of stimulus, whether it's an auditory, visual, somatosensory, or olfactory, you will have a region within your squid cap to capture an enhancement of either an electrical signal or a magnetic field signal in that region that has been activated. You can also have other tasks. So for example, if you're trying to ask somebody to imagine something, or if you're asking somebody to respond to a certain stimuli, then those are reactions that can be recorded as well to see what parts of the brain are activated for those types of responses. So what kind of equipment on your head? What kind of equipment is placed on your head? You basically are sitting here with your squid cap, and zooming into this squid cap, we have an MEG measurement region with a squid sensor. And so the magnetic field is going to come up from your head, and the squid is going to sense it and then process a signal. You then have within each sensor a feedback coil that allows measurements to be taken and processed. So what we call these are pickup coils. There's a single coil called the magnetometer. It's equally sensitive to both the magnetic field and B naught, which is the external magnetic field. You have the axial first order gradiometer, and that is 2 separate coils wound in an opposite direction. Very important to know. It's only sensitive to the spatial gradient of the magnetic field. You then have a planar gradiometer, and that has the same principle as above, except 2 coils are now placed side by side, and its main purpose is to increase the signal to noise ratio. So between all of this, we can understand that it takes a lot of effort and a lot of work to help amplify a signal and to make sure it's a clear signal coming from the head when you're using MEG techniques, because there can be a lot of noise involved, especially when we take a look at any spontaneous currents that take place within the brain. So let's go through a summary. We're just going to go through some key concepts and important equations. In this lecture, we learned about the magnetic force, the magnitude of the magnetic force, which is just basically the cross product, the electromagnetic force. We were able to figure out the cyclotron frequency, the radius of circular orbit of a charged particle if we make sure we can set the velocity for our situation and scenarios. We have the magnetic force on a current. Of course, we have the Biot-Savart Law, an equation for the magnetic force between 2 wires. And we also have Ampere's law, which is the most important. And based on Ampere's law, we can then easily derive the equation for a solenoid field and for a toroid field. So these are equations that you can just use based on the situation and the question that you're given.